Hi friends, welcome to our channel. Here we are going to look at problem 3520. This is a newly appeared problem. It's called minimum threshold for inversion pairs count. So here in this video, we are going to use sorted list to solve this problem. So after seeing the code, you will see, so this is the natural data structure to address this problem. So here, before we do the coding and also make a remark, so you can try to solve the problem using heap or using segment tree plus binary search, right? So with that said, let's look at the problem statement. So we are given an array called nums and an integer called key. So here it defines a inversion pair with a threshold value x. So basically it tells us it's an inversion pair such that the difference of the two numbers is bounded above by x, that is less than or equal to x. So our task is to determine the minimum integer such that there are at least key inversion pairs with this integer threshold. If no such integer exists, we're going to return -1. So here the length can be as long as 10 to the power 4. Therefore, we need to take time complexity into consideration. So with that said, let's quickly walk through exercise 1 so that you know we should use binary search, right? So here k is 7, so we want to have at least k equals 7 inversion pairs. So here let's first examine the inversion pairs. So 1, 2, 3, 4, they do not produce any inversion pairs because they are forming a strictly increasing sequence. So now if you look at this 3, so it can come with this 4 to form a inversion pair. So we have 4, 3, but no further, right? You cannot further go left. So when you look at this 2, so you can come them with 3, 4, 3, right? 3, 4, 3, right? So let me first delete this. And then if you look at this 1, you can go left to 2, 3, 4, 3, and 2. So these are 5, right? 5 inversion pairs. So those inversion pairs, we didn't consider the bound, or you can think x is infinity. So when x equals positive infinity, so then the number of pairs is 1, 3, and this is 5. 1, 3, 5, that is 9, right? It's greater than k equals 7. So we can shrink this x. So in this example, the answer is 2. So let's try to use 2. So if you use 2, the difference should be less than or equal to 2. This is the 1 pair, and this is 3 pair. So because there are difference, this is at most of 2. But you cannot include the 4 here, because 4 minus 1 is 3, right? But 2, 3, 2, 3 are okay. So 4 pairs. So in this case, you get 1, 3, 4. That's 8 pairs, still greater than 7. Can you further decrease x? No. If you try x equals 1, so this is the valid 1, but this 4 is not valid. 4, 2 is not valid. So you get 2 pairs for x equals 1. And again, here you have 1. So because your x is 1, so you get 2 and 2. So you have another 2 pairs for x equals 1. So in total you have 1, 2, 2, that is 5. So this is less than 7. Therefore, your x is to return is 2, right? So this is the shrinkage. So now we know there's shrinkage, and there's a check if it's greater than 7 or not. So this is exactly the binary search pattern, right? Recall that in binary search, so if you're not doing vanilla binary search, typically what you need to do is to define a Boolean function to produce monotonicity or order, and then you do search range shrinkage, right? So if you are not familiar with this pattern of use, you can check out our playlist for binary search in the channel. So with that said, I guess this should motivate you to do binary search. So now we want to use a data structure to get this, because here the order is important. So for each number, see, we want to find those which is larger than this number, but not too large. It's upper bounded by this number plus the x, right? So we're going to use a sorted dict. So because sorted dict, they have a method called bisect left and bisect right. So, and also in this regard, we consider the reversed array. So this makes the sorted list stores larger indices of the original array, right? Because for example, we store those numbers. So those numbers corresponding to larger indices. So you need to keep in mind that for inversion pairs, larger indices correspond to smaller numbers, smaller values. That's an important thing. So our plan will be the following. We first do the coding next, and then we digest after the coding. So first step, so define a Boolean function. So here let's define it at least k, right? So we accept the x, so which is the integer, so we want to return a Boolean, right? So we want to have a count variable, which is count the valid inversion pairs, and then we initialize a sorted list. So the sorted list. And then what should we do? So basically we are going to iterate in a reverse fashion for y in nums reverse. The reason is that we store these numbers, but those numbers corresponding to large indices. Large indices will correspond to smaller values, right? This is important. This is crucial for the problem logic. So now what we do? So we count. So we want to see if we use the current y and with the pre-stored numbers corresponding to larger indices, how many valid inversion pairs. So we know for those we want to find values such that they are smaller than y, so they should strictly smaller than y. Find values a such that a is less than y, but a should be not too small. So y minus x is greater than or equal to y minus x. So this is the range. So we are going to first do this. So sorted list. So bisect left. So nums, not nums, that's y. So this will give the number of elements, the count of elements that is strictly less than y, right? Then we need to minus those bisect left y minus x. So this gives us the number of elements that is strictly less than y minus x, right? So in other words, this count, so let's see, count, I'm going to use a set. So the count or the set of this equals, so this is actually some set decomposition. It's less than for a strictly less than y. So minus for those a strictly less than y minus x, right? What you left is those greater than or equal to y minus x and less than y, right? So this is exactly the thing we are doing. So once you have this, then you see if k is if the count is already greater than or equal to k, we can do an early stopping. So we just need to return true. Afterwards, so we need to, so here we always add the nums, right? Add the y. So finally, we just need to return if count is greater than or equal to k. So this is our Boolean function, right? So next we do search range shrinkage. So this is actually very simple. So first I want to treat an edge case. So here the range. So let's see, the range will be the max of nums minus the mean of this nums. So right, so here I'm adding 1 because this is the bound. So if this is the largest possible bound. So if this number if not, at least key the bound. So if this, even you choose such a large number, you still cannot produce key valid pairs. So you just return -1. This is the case. So otherwise, so what we want to do? So basically, we can return. So we want to do bisect left, right? So here, given this range of this bound, and then so we are going to use the key to be at least key, right? So this is the one way to get this. Let me first write it, run it to see if it works. At least key. So here, at least. Yeah, it passes the two cases. So now let's look at the generic case. Yeah, it passes the generic case. So the first comment I want to make is that this is actually very compact. So now let me delete this part or comment out, and then we write some using the general way. So basically, we want x to be so we want, let's see, what's the x? The number is at most x. X is greater than 0, right? So low is let's see 0, and the high is so the largest possible. So the largest possible, we can use infinity even. So let's use this RG, right? So basically, well, low is less than high, right? So we get the mid is low plus high minus low over 2. So we check if at least key mid. If this is true, right? So in other words, we can try to shrink it further. So we can have high equals mid. Otherwise, so if this is not right, so we need to make the bound larger. So we set low to be mid plus 1. And then we just need to return low in this problem. So now let's run it. Yeah, it passes the two cases. Now let's look at the generic case. Yeah, it passes the cases. I guess for this one, if you do bisect left, so this is in the module. So if I write it more clearly, is bisect left, right? So you need to do some manual check, but here it's roughly from scratch. But you can try also say infinity, say, or very large number. Let's see the largest number. So we can use max, or we can use max nums, right? So it should be still okay. Yeah. Yeah. So that's actually the power of binary search. So I guess let me also check this one. So because here, if the largest one, the smallest one, so it's max and min. So this is the largest this difference is the largest possible difference. So you can actually write it like this. So it should be fun, right? Yeah. So I guess this is not very rigorous, but it's good to understand the idea. So here, this will be the range of the difference. We need this is the maximum possible range can be yielded from the difference can be yielded from this given list, any given list. So here, actually, we use this. You can also use this RG, right? Yeah, I guess with that said, that's basically about it for the current coding part. So let me make some remark. First, if you look at if you had chance to check my previous videos, so I have made a comment that for a problem, if you can solve it using sorted list, typically you can solve it using min heap. So you can try to solve this problem using min heap. And another thing is that in the hint of this problem, so it suggests that we use a segment tree. So you can also check out our video on segment tree and binary index tree, or also called Fenwick tree. That's also be good exercise, right? So this is the one comment. Another comment is that the pattern of using binary search. So typically you need to define a Boolean function like here, and then you do, let me mark that, you do search space shrinkage. So this is the second comment. So we have a playlist which accumulates quite a large number of problems which can be solved using binary search in this pattern. Hopefully that playlist can help you practice. So this is the second comment. The third comment here is that in this problem, it's important to reverse the array, right? So because we want to first store the numbers corresponding to larger arrays, and they correspond to smaller values, and then we can do the search using bisect left and bisect right, bisect left. And when we do this, in order to better understand this, so we used some idea for set decomposition, right? So this line here, star, corresponds to this line here. So this is the third comment.